So, we are looking at modes of internal variability because they can begin to also work at time scales. We are looking at global warming, and as we said in the very beginning, climate change is a very general term. Change at what time scale? There are changes happening from year to year, decade to decade. So now when we say climate change or global warming, we are generally implying anthropogenic time scales, which is basically since industrial revolution. So we are talking about century time scale. So we looked at the El Nino, which is typically known as El Nino Southern Oscillation. So the term is ENSO, not as evocative as El Nino. You can use them interchangeably. ENSO includes both El Nino and La Nina. So people call it warm ENSO event, cold ENSO event, and so on, but that's a detail that you can remember. So there are other modes of variability in the Pacific. I will show one in the Atlantic next. So El Nino looks like this, where we have a narrow band of warming, and it turns out that actually the warming can be more focused around the dateline and include the coastal region or not include the coastal region. That matters because if it doesn't warm here, then the amount of heat taken up by the ocean will be very different. So I will show that a couple of slides down. And there is a mode that looks almost like an El Nino, but has a much broader scale than El Nino. You cannot even tell the difference here, but more importantly, it has a decadal or multi-decadal time scales, which means it has got 10 to 30 year scale. So you can see that El Nino happens in short bursts, typically last for 9, 12, 18 months, whereas the Pacific Decadal Oscillation, affectionately known as PDO, tends to survive for 30 years. So it's in the warm phase here, warm phase there, and right now we were in the cold. I think we are flipping now. So you have to be careful because it can go into a positive phase and come back into a negative phase. But essentially it has a much broader spatial scale and much lower frequencies. We don't always know what causes these climate variability modes. El Nino we understand a lot. As I said, something happens, trade winds weaken, upwelling reduces, and then there is a positive feedback between sea surface temperatures, winds, upwelling, convection in the atmosphere, and so on. Pacific Decadal Oscillation, we don't have such a solid theory, but nonetheless, like many changes we saw in the paleoclimate records, this one exists in the data, and we know it shows up in terms of impacts on fisheries, drought over US, even relationship to monsoon, and so on and so forth. So it is something to worry about. And if you have Pacific Decadal Oscillation in the positive phase, obviously it has got a negative or positive temperature signatures over a large part of the globe. So remember, Pacific occupies quite a bit of the ocean of the planet's surface. So can imprint on global warming. The other one is the so-called North Atlantic Oscillation, affectionately known as NA. You are a teacher and you can throw out words like PDO and NAO and ENSO. People will think you are an expert, so that's always good to remember. So there is a semi-permanent low pressure system over Iceland, Greenland, that's called Icelandic low. Over the Azores in the subtropical region where the Hadley cell comes down, the high pressure known as the Azores high, and over several time scales from year to year, from decade to decade, this pressure oscillates between, this one becomes anomalously low, this becomes anomalously high, or vice versa, and there is also a polar pressure there which kind of interacts with these. So this oscillation is called the North Atlantic Oscillation, and depending on how strong or how weak this pressure gradient is, these large scale winds, the mid latitude westerlies, change direction a little bit. There is a relation between pressure and how fast the currents move and so on, there is a separate module on so-called geostrophic currents that you can look up, and that kind of plays into this. But just to remember, Icelandic low, Azores high oscillating on multiple time scales, which determines which way the storms go. If it is going over Europe, then the climate over Europe changes into mild and more rainy, and if the storm track goes north, then the lower part of Europe gets drier and warmer, and the upper part of Europe begins to get stormier, milder and wetter. So you can see that this also can play a role in modulating global warming. So it also survive for decades. So there are cold phases and there are warm phases, and you can see that there can be rapid flips on interannual time scales as well. So these are kind of the main modes of variability that I will mention. There is a similar one in the Southern Ocean called SAM, or Southern Annular Mode, which is very similar to the North Atlantic Oscillation, which also sometimes called Arctic Oscillation or Annular Mode, because they affect the entire circle around the latitude where they occur. So it is in this context. So coming out of the deglacial, continents moving, ocean basins moving, sea level rising because of the melting glaciers, and we are adding lots of anthropogenic greenhouse gases. We are changing the land use and so on and so forth. So I will begin to go through what are the observations we begin to use now in this modern era, what are the evidences we have, and how we relate the evidences of changes in radiative forcing to changes in various observed quantities, not just temperature anymore, but we will get into looking at impacts on agriculture, health, ocean temperatures, sea level, crops, and so on and so forth. And because eventually when we want to deal with climate change into the future, basically want to worry about things like food, water, energy, health. Of course, many countries will also begin to worry about national security, which I will mention in the context of global warming. So when did we begin to know it? If you remember the famous Keeling Curve, which I will come to in a minute, the carbon dioxide data over Mauna Loa in Hawaii began to be collected in the 1950s. Within 10 years, it became obvious that the carbon dioxide was beginning to increase. In fact, as far back as 1876, Svante Arrhenius, a smart chemist, said that we are burning now so much coal that the carbon dioxide in the atmosphere is going to dissolve into rain and begin to warm the surface. So he was one of the first ones to say that industrial revolution is going to start to change climate. And in the 1920s, the people like Vernadsky and so on, who began to introduce other concepts like biosphere and how biology affects geology, etc. And Wegener's continental movement theory came along, which allowed us to go back and look at climate changes in the past in a different way, etc. But essentially in the 1920s, the data began to show that the global temperatures were beginning to rise. So these are two different data products. We will keep on looking at different products because they don't all show exactly the same. So the question is always what do the differences mean, and whether they really change the scientific conclusion about either global warming or the cause of global warming, and so on. But they are important because regional differences can become very important, as you will see with a few examples. And becomes very critical when we come to rainfall, because rainfall is very hard to measure, and we'll come to some more details of that. So this report that the IPCC, I think most of you now know what is IPCC. It is the Intergovernmental Panel on Climate Change, which was formed under the United Nations Framework Convention on Climate Change. So it should be actually another C, I think. So at some point, the world came together and decided that we are perturbing the climate in a large way, so we must form a committee where the scientists will get together. They will collect all the evidence and together, and they will build models and make model simulations of the past and the future to see what the past is telling us in terms of the impact of human beings and what that means for the future. So they made a projection somewhere here around. This report was released in 2001. So you can see that they had made projections into the future. So we are now looking at few years later, and the model said the range of warming will be this much based on how much carbon emission assumptions were made, population assumptions, vegetation change assumptions, etc., etc. And you can see that the observed change that did occur that time is basically within the envelope where the model said the warming will happen. So it gives you some confidence that the models were able to reproduce the observed warming over the 20th century, and they were projecting the right range. What does this mean for the future? We'll keep coming back and looking at it again and again. So as I've said before, the models must reproduce past variability to be able to trust them for their projections of the future, even though many assumptions are made about the future. This is why multiple models are used and a range is provided instead of saying it's going to follow just this. There are many details. For example, if the model started with a slightly different conditions of temperature, humidity, and vegetation, and so on, Mother Nature can go in one direction and the models can go in a slightly different direction. That's called dependence on initial conditions, which becomes very critical in weather forecasting, climate forecasting, and so on, but also could play a role in climate projections. Kind of details, but you should be aware of those things. So here is the famous Keeling Curve. Charles David Keeling started collecting data because his advisor Roger Revelle at Scripps Institute of Oceanography in La Jolla told him that would be a good idea. What a great idea it was, in fact. So the showed that there are these ups and downs, which are basically the arrival of sun into the hemisphere and spring blooms and photosynthesis starting and drawing down the carbon dioxide, mostly over the northern hemisphere because that's where most of the land is. And in the fall months, when the trees shed leaves and photosynthesis drops, for winter months, then the atmospheric carbon dioxide increases. So this is the, you can think of it as the planet breathing, but over that there is a clear signal that carbon dioxide has been increasing, and at the current time we are actually over 400 parts per million by volume. So we started in the industrial revolution with around 280 pp. Now we have gone up to 405 or 6 by now, and each year it's increasing by about. This is important because we need to look at the rate of change and compare it to past rates of change, and then see what can we learn about climate sensitivity, which means when you increase carbon dioxide, how does our planet's climate respond? We can only learn it from the past because models, we will see that models will tend to have slightly different sensitivity than nature because the models do not capture all the details that are happening in the natural climate system. So if you look at the changes going from 1980s, 90s to the previous 10 years, you can see that the increase in carbon dioxide, it kind of dropped. There are many reasons why it will drop, I will show in a minute, but it has recovered. So the number of parts per million by volume, that increase is happening, itself is increasing. So if you draw trends, the trend of increase is increasing. Okay. So we will look at these in multiple ways, just so that you completely get comfortable with understanding the changes in the forcings and the associated change radiation at the top of the atmosphere. These are kind of the critical links you have to be very comfortable with to explain the rest of this. Okay. So fossil fuel and cement production also increasing each decade. Ocean atmosphere exchanges increasing, which basically means if you increase carbon dioxide in the atmosphere, ocean should take up more. But the question is, will it continue to take up more, or will it saturate, or will the winds change in such a way that how much gets mixed into the ocean reduces, or if rainfall changes, will that change the amount of carbon dioxide that can go into the ocean, and so on and so forth. So the carbon story, sources and sinks, gets quite complicated, and we will see it in many different ways. So the land atmosphere, again, we will see that this is also a complicated story. There are some good knowledge about where the carbon is going and where it's coming out, but there is also some places where we don't know exactly what's happening. So we will see what those are. Land use change. So we are basically converting land by converting to agriculture or urbanization and so on. So land use, remember I called it LU, land use, land change before. That is definitely increasing the contribution into the atmosphere. And there is a bit of global greening going on, reforestation and so on. So we will look at one map where in fact even India may its forest cover and reducing its emission of carbon dioxide. So all these sorts of things together give you this. So these are very difficult to figure out, but this is very easy to measure. You can measure it precisely and accurately again and again and get the same value, and you can compare it to a standard and it's highly accurate. So this is the good news, that carbon dioxide, which is well mixed and has a long residence time, can be measured very accurately. And some of these things are more accurate. For example, fossil fuels and cement production, these are commercial products. They are tracked very carefully. How much coal is produced, how much is sold, how much cement is produced, how much is sold. So these emissions can be much more accurately computed or measured than the other contributions from exchanges between the ocean and atmosphere, land and atmosphere, and so on and so forth. So you just should be aware of where the uncertainties are. So everything matters because these greenhouse gases are providing radiative forcing, which means they are changing the balance of radiation at the top of the atmosphere because they are greenhouse. And this is why climate changes, and this is why we worry about it. If they didn't change radiative forcing, we probably wouldn't worry about it, but you have to remember that it's all pollution. So since the 1970s, we know that impacts of pollution on been quite severe, and they continue to be quite severe. So it's not just that we need to worry about global warming, we also need to worry about the impacts of air quality, water quality, pollution of groundwater, etc., and poisoning of the fishes with mercury, and so on and so forth. So if you compare just look at examples of radiative forcing, we'll again come back to these again and again just to make you comfortable. Look at the various contributors to the radiative forcing. The estimated 2005 radiative forcing by carbon dioxide, methane, halocarbons, which is basically refrigerants and so on, that I will show a figure of. Nitrous oxide, which is mainly an emission from agriculture, which is a very strong greenhouse gas, almost 200 times as strong as carbon dioxide. Aerosols, we will see animation of how dust particles and chemicals like sulfates are being produced, and many of them basically block sunlight. This might sound like a good thing because they will cool the climate. They make lots of problems for processes like the monsoons. So when we have a monsoon lecture, we will come back to looking at the impact. Basically, aerosols, very quickly, more dust you have in the atmosphere, more the cloud condensation nuclei. I think I mentioned this before. If you have lots of cloud condensation nuclei, then the rain then tends to drop as drizzle instead of bigger droplets and rain. So actual amount of rain can change, and the blocking of the sunlight, which is called the direct effect of aerosols. There are all these indirect effects of aerosols about changing cloud property, cloud brightness, amount of rain, duration of and frequency of rain and so on and so forth. Okay. So, this is the indirect effect, aerosol indirect effect. By urbanizing and deforesting and changing vegetation, agriculture, etc., we are changing the albedo of the land surface. The best estimates in 2005 were that we were essentially increasing the albedo, so we were cooling the global climate by providing a negative radiative feedback. But you should always keep an eye on the uncertainties. Here it's saying minus 0.10 watts per meter squared. The uncertainty there is plus minus 0.3. So, the uncertainty is quite huge. We will see that. And this is associated with the level of understanding as well for each process that will show a plot. So, you can see that we not only have to estimate these, but we have to provide a very solid grounding of what are the uncertainties in our estimates. So, the air transport effects, the so-called contrails, I will show a figure, has a huge impact. Other than the emissions, also has contrail effect. Solar irradiance itself has changed. So, you can see, as I have said repeatedly, that contribution is fairly small, but it also has a certain level of lack of understanding or uncertainty in it. So, these are kind of things we have to keep worrying. So, in that context, again, let's look at where we have been getting our evidences from. Shells that preserve past temperature records through L02 and so on, speleothem, tree rings, corals, etc. And as you go in the past, the uncertainty can increase because you have no direct measure. You are estimating or reconstructing past temperatures using these proxies like calcium carbonate shell. And oftentimes the data is from individual locations. You can collect as many locations as possible to reconstruct the global mean, but depending on the method and the location of the amount of data, number of locations, etc., you can obviously have very different estimates, not insignificant. But you can see that as we come into the post-industrial era, especially the 20th century, the uncertainties, the spread of the different estimates begin to reduce, and the warming is again beginning to go beyond whatever the spread we had in the past. This message I will repeat because you have to convince yourself that the signal that we are observing of global warming is actually beyond the noise. If you think of the spread in the past as noise, the signal has to come out of the noise. Okay. Let's touch on a few sources of data we use. So, this is a nice animation of the ocean color which shows the seasonality at high latitudes and the seasonality here. So, the upwelling itself has seasons. We kept saying there is upwelling, but it's weak during the spring months and it's very strong during the summer and fall months because the trade winds themselves change in strength. The upwelling and the Ekman divergence itself changes in strength. Here, as the sun comes overhead, there is light and there are nutrients. So, the bloom happens during spring and summer months. At high latitudes, in the late fall, winter, there is no production and so on. This is showing precipitation. Again, we will see an animation of the Hadley cell, but you can see where the rain bands are and where the downwelling branch of the Hadley cell is. That also moves seasonally. It's a nice way to look at movement of the whole system. And the sea surface temperatures themselves obviously also move because if the upwelling is getting stronger and weaker, that means the winds must be also moving. The tropical convergence zone itself moves, as we will see in animation. So, the warm water itself goes from the southern hemisphere into the northern hemisphere and back with the sun. So, as the sun moves, the entire system is moving back and forth. So, that is the radiation. Obviously, in our winter, radiation is more in the southern hemisphere. As we go into spring and our northern hemisphere summer, the radiation is more. So, the satellite data that started to be collected more and more since the late 70s to now provides incredible global coverage. This you cannot do with individual proxies and so on. That is an advantage. But there are many disadvantages. For example, the ocean light cannot be penetrating too much which means the satellite can only see the top few meters to 100 meter or so, and it cannot see what's below the surface. As we will see, what is happening deeper in the ocean is one of the most critical things to understand for global warming, because 90% of the heat and a lot of the carbon dioxide and so on are going into the ocean. So we must understand how the ocean is changing. Okay. In that context, we can show that the amount of fossil fuel burn is going into different partitions. So if you go back to our Keeling curve and look at it a little more carefully, it is not increasing as linearly as it would appear when at the long time series. Essentially, you can take out this trend and then it will show the year to year variability of carbon dioxide that remains in the atmosphere. So what does it show? Basically, it shows what we said before. When we have El Ninos, remember the upwelling is reduced, so the CO2, carbon dioxide coming out of the ocean in the Pacific is reduced, and that's a huge contribution. So during an El Nino, there will be reduced amount of increase in atmospheric carbon dioxide. Outgassing from the ocean will be reduced, and when it is a La Nina or normal times, it will increase, and the percentage of airborne fraction is shown here. Basically, what we observe in the atmosphere can be measured very accurately and precisely, but it is only a small fraction of the carbon dioxide we are emitting. That's what we have to remember. So sometimes as little as % is in the atmosphere, sometimes as much as 80% is in the atmosphere. So we must understand these changes and also figure out where it's going and how it's changing over time. What are the sources, which means what are putting CO2 into the atmosphere other than fossil fuel burning and so on, and where the carbon dioxide is being taken up, how long it will be kept there, and so on and so forth. So this gives you the context of carbon dioxide change. Again, carbon dioxide estimates are fairly reliable because we are getting them from bubbles in the ice cores and so on, and because carbon dioxide is well mixed, whether you measure it in Antarctica or Greenland or somewhere else, you get a good estimate of carbon dioxide, unlike temperature or precipitation, which can be very local, right? That's why you have much less uncertainty going back, and you can see that we were at the deglacial level for a while. There were some human impacts, but since industrial revolution, we have grown super exponentially. So the increase in carbon dioxide is very clear. So in terms of exchanging the causes for climate change, we have to put this story together. How has carbon dioxide increased? Is it beyond natural variability? If so, does that explain the warming? The estimates, I will show this kind of figure over and over again. The land clearance for conversion to agriculture or urbanization has contributed and has contributed more and more over time. Fossil fuel burning also has increased more and more over time. Coal is still being burned, which emits more sulfates, and it's dirtier than petroleum, which is dirtier than natural gas, and so on and so forth. All these things we must track. The budgeting of carbon is a very tedious task, and it is done every year. So you can see that this is an average over around 10 years, 2007 to 2016. Again, we have a very good idea of how much fossil fuel is being dug up and burned. The amount of carbon dioxide put into the atmosphere by burning coal, petroleum, gas, etc. is going up year by year as economies develop, like China and India, Mexico, Brazil, and so on. Their emission keeps going up, but the big giants like the US and Europe have been emitting industrial revolution. The growth of CO2 in the atmosphere itself is also increasing, as we said already. Land use change, positive input into the atmosphere with fairly significant uncertainty, almost more than 50%. There is a sink which is basically something like carbon fertilization, which means as you increase carbon, the trees can grow faster and take up more carbon. So there is some estimates that say that the land is taking up more carbon, and the ocean sink is estimated to be about 2.5. All these are in gigatons of carbon per year. So that's the average over these years, and each one has an uncertainty, as you can imagine, and we will see the figure where it shows that you are often comparing two large numbers. There will be like 90 gigatons being taken up by the ocean, but or 92 gigatons taken up, but 90 will be respired back. So you have to measure very carefully so that the small differences between two huge numbers are estimated to be the actual taking up of the carbon or emitting of the carbon. Beyond all that, there is still an unexplained sink which is about 0.6 gigatons per carbon. That's a imbalance in the budget. This is often referred to as the missing sink, and the way to look at these in this context is that you can see over time how things have changed. So here again is tons of CO2 per year. You can convert CO2 into carbon by taking basically the difference in the weight. The multiplier turns out to be 3 point something, which you can easily work out. So when you deal with different types of carbon like petroleum, coal, and CO2 in the atmosphere and so on, often it's easier to convert to carbon or call it equivalent carbon and so on. So these units are used interchangeably, but there are multiplying factors which you should be aware of, which will be provided in the resources. So here are the emissions. The emissions due to fossil fuel obviously have gone up continuously. The land use change contribution has increased, but maybe somewhat stabilized. And as far as the sinks are concerned, as we said, there is the land sink, which is usually just a residual. So I don't think we have a very good handle on the land sink. Just often assign the imbalance to land use, uptake by the land. Okay, and the atmosphere obviously accumulating more and more because the ppm in the atmosphere is increasing from 280 before industrial revolution to more than 400 now. That is shown here, and the oceans are taking up more and more. The question always is, will these sinks continue to take up? Because remember, this is what we are worried about. What remains in the atmosphere is going to give us the radiative forcing, and if it is hidden in the ocean, the other question will be, will it be emitted back like the heat it's being taken up and so on. But nonetheless, these are the sinks, those are the sources, and they are changing over time. So what does the ocean do? Again, you can now use your circulation knowledge to relate to the cycle. So we said there is strong upwelling here, and we said the CO2 profile looks like it's low near the surface and increases with depth. So if this is the surface and this is depth, so if you upwell, you are bringing up more CO2 from below. So the partial pressure of carbon dioxide in the surface waters goes up. So it is emitting carbon to the atmosphere, and this is a large fraction of the global surface area. So it puts out fairly significant amount of carbon dioxide. Here the unit used is moles per meter squared per year. So per unit area per year, how many moles of carbon dioxide are being put out. There is a similar upwelling here. The Indian Ocean, we said, has more upwelling here because of the monsoon winds, and there are regions where carbon dioxide is going into the ocean. You can see North Atlantic is a huge sink, and the Southern Ocean regions are huge sink. Why do we look at this? Basically, with global warming, you have to understand how the winds are changing, because how much carbon comes out or goes in depends on wind, but like a wind speed cubed. So it's a very non-linear effect. How the temperature is changing. If the warming happens, partial pressure increases, so solubility decreases, so CO2 will escape. It's like the Coke. You keep it cold to keep the CO2 buried inside. If you leave the Coke in a warm weather, it's going to release the CO2 and it will lose, right? So those kinds of things are working here. So not only winds changing, but we don't know how El Nino itself will change with global warming. This is a very difficult question. Really understand how El Nino might respond to global warming. So as we change Atlantic meridional overturning circulation or the global thermohaline deep water formation, especially because Greenland is melting and so on, what will happen to where the carbon dioxide is going into the ocean? That's always critical to understand. So this is one figure which is showing the mean sources and sinks of carbon dioxide. Because there is so little data, we can take all the data and produce only like a mean map. How these are changing over time is very well understood because we don't have a lot of data. Regions for this, for example, it's very hard to go there. In the winter, you have things like furious 40s, storms are very strong, and I don't know, screaming 40s, I think, furious 50s, and or roaring 40s, furious 50s, screaming 60s, and so on, which means the ships only go there in the summertime, in their. So the winter oftentimes has no data. So you can have a lot of issues on estimating how much carbon dioxide is actually going in, but we are fairly confident that carbon dioxide is actually going into the ocean there. How it's changing over time is a more difficult issue. These are concentrations of various halocarbons, so include chlorofluorocarbons and other forms, CH3, CCl3. So obviously CFCs were banned after it was realized that they are not good for us because they were forming the ozone hole, which had become very obvious over the Antarctic subcontinent, again because the circulation here could trap the air, trap the chemicals, and their residence time would go up because they couldn't get out of there or mixed away. So the ozone hole kept getting bigger and bigger, and then Montreal Agreement happened. Since then, the tons of CFC production has dropped, and the concentration of ozone, which is measured in something called Dobson unit, which you should look up, was increasing, and now it has stopped increasing. So the minimum ozone or the ozone hole is not growing anymore. There is some indication that maybe it's recovering, which means the ozone may be going up. This is, if you want to think about philosophically why the world came together and agreed to reduce CFCs in the Montreal Protocol, but the world is having so much trouble agreeing on anything for global warming, you should realize that increased CFCs destroying ozone was harmful. There was nobody who is going to be safe from reduced ozone, because if ozone reduces, more of the UV radiation, ultraviolet radiation comes into the lower surface, and we are all susceptible to UV, skin cancer, and so on and so forth, right? But with global warming, we will see that there are places where rainfall will increase, increased temperature will be beneficial, and so on and so forth. So global warming will create winners and losers. So nobody is sure whether they should spend money on global warming or not. But tropical countries, unfortunately, already are experiencing extreme events and so on, which we will look at. So who will benefit from global warming, who will not, is not clear, but it's clear that if Siberia gets warm, maybe they will start growing more wheat and they will be just fine. If we keep getting warmer and warmer, maybe we will not be able to grow anything, just heat waves and deaths every year, right? So those are the kind of questions we have to worry about. I will stop with this, which is showing the various sources of methane, which is another important greenhouse that has increased over the last 200 years or so since the Industrial Revolution, and it comes from all the swarms. Termites are a major source of methane, and our beloved cows are ruminants, so they eat a lot of things. They have a separate chamber for it, and then they regurgitate and chew them. So it's a thermodynamically incredibly inefficient process, but also produces a lot of methane. And of course, our favorite food, rice, the way we do the rice paddies, they are huge sources of methane. These are the sources of methane, and we will see how the methane is increasing when we come back. So see you next time. So essentially, we are now looking at the forcings that are changing over time and how we can use the data to show that they are the causes for warming. I haven't shown a warming picture yet, but we will get into more pictures or more data showing global warming, which means temperature averaged over the whole globe, and patterns of warming. Where is it warming, and are there places where it's not warming? We'll get into other effects. Okay, see you next time.